Hear me? I'd like to make sure. So, okay, thank you. Hey, so let's get started. Good afternoon. So, how are you doing? It's cold. Okay. So, this is the syllabus. We have just couple of weeks. Then, as you can see, and this week and next week, we will talk about the physical database design. And the following week, it's a Thanksgiving holiday, so all weeks we don't have class. And then the last week, as you can see, the due date, the final project, and then final reflective assignment, and then student course evaluation. Okay, so keep in mind the assignment or the task and the place complete and the submit by the due date. Okay. So assignment 6 and discussion 6, due date is November 21st. Okay. Not open yet, but maybe in the Thanksgiving week I will open. Okay. And also student course evaluation will be emailed to your MGA email from the MGA, the university. Okay. So this chapter is a physical database design. So far we learned the logical database design. What is the purpose of the logical database design? Do you remember? Two main things. Logical database design is to make table into normal forms. First, second, third, BCNF, fourth. Yes, correct. That one. And the second one is to remove anomalies. So modification anomalies such as insertion, and deletion, and then update anomalies. So using the logical database design, we are able to achieve two goals, but physical database design are a little bit different. We have to think one more the factor that is called the performance. Okay. So this chapter, we will describe what is a physical database design. And I'd like to remind you how a disk, the hard disk drive works. Okay. And then what is the file organization and then access method. And then simple linear index and then P plus tree index. What are they? The hashed function, hashed file like this. So as I said, so in the logical database design, reduce redundant data and then try to remove anomalies. But one more thing, we have to think what performance. For example, if we have the long table and then using the logical database design, we split into the small and maybe BCNF forms and the force forms like that. But, and then redundant data are removed and then there's no anomalies each the normal forms. But using that, the tables when you send the query to select, to retrieve, to find, or update, maybe it takes about 1 minute, 10 minutes, just for the single query. What do you think? It is a good performance or bad? So bad. Just one single query, 1 minute, nobody uses that database anymore. Maybe less than 1 second. Makes sense, right? So we have to consider the performance. Usually performance can be measured by the time, the return time when you send the query, and then the time you get the result. So we have to consider performance. Okay. So to do this, to improve the performance, there are several techniques. For example, adding index to the normalization. Okay, so today I'd like to mention about the index to improve the performance. So in terms of the performance, there are a lot of factors affecting application and database performance. So first of all, application factors such as a lot of joins and a lot of aggregated functions such as summation, average, to find the maximum, minimum, and so on. Or the join. If you have multiple tables to find a specific row and record data, if we have a lot of joins like that, it takes time. Why? Basically, the join is working on the Cartesian product. Cartesian product is if there are 10 record and 10 record, each row in the first table is trying to match and define the matched record. In this case, foreign key and primary key. And go to the next row and then multiply. Go to the next. So total 100 operation we need. For example, but extreme case, we have 1 million records. 1 million. How many operations we need? 10 to the power 12 operations are needed. It takes a lot of resources. So if we have a lot of join, it takes a lot and takes a lot of computing resources. So it affects the performance here. And then large data volume, 100 row, compare 100 row versus 1 million. Absolutely, obviously 1 million row takes a lot of time, okay? And then lack of direct access. So in order to find or locate the specific row, so basically two methods. One is a sequential access and then direct access. You know that sequential access is from the start, from the first, and then compare that data is that I want to find, want to retrieve it. If not, go to the next. This is a sequential. But direct, if we have some address, we don't have to search from the first. Go to the specific location using some data, some information. That's a direct. So if we don't have the direct access, it also affects performance. And then multi-attribute primary key, but if they are clumsy. So if you select the primary key, should be minimized, minimum column. Maybe there is a salesperson ID, name, and address, and then commission of percentage, and so on and so on. So usually the salesperson ID is a primary key, but we can add ID plus name. Also, these kind of composite key can be used as a primary key, but this one is not necessary. So if unnecessary kind of redundant, the column is used as a primary key, it takes computing power for processing your request, especially join and the summation and so on and so on. Okay. So design the primary key, the minimum the column as a primary key. And then physical vector is the data physically displayed on the disk. So that is a secondary, the hard disk drive. One is that here, sales ID here, so store there, but maybe name is stored there. So physically, to find from here to that data, it takes time to move. But to the I'll show the ARM mechanism in the hard disk drive. So in order to avoid to reduce the searching time, if we store related data as a cluster, but in that case, we can reduce the searching time. It's a physical factor on a disk. Then too many data access operations to the same data. So, and then giving people access to more than they need. So those kind of the business environment factors also affect the performance. So when you design your database, you have to consider all of them, okay, for the better performance, the optimal performance, okay? So the definition of physical database design is process modifying database structure to improve performance. So in the physical design, we may modify normal form table. In a logical database design, we split into the high order relation, a table. But sometimes to improve performance, we combined the tables. That is called denormalization. It's a kind of the opposite direction. Okay, logical database design, remove redundant, remove anomaly, but performance bad. In that case, we combined. So there are some redundant data, and then there are some anomalies. But if the performance is better than the previous one, we can use that one. Why? The performance is more important factor. Okay. So run faster. That's a keyword. The performance. So have we ever seen before CPU architecture? No. So when you open up the laptop or desktop PC, and you can see the motherboard. So basically, there are the memory, and then CPU, and then input, and the output, and another one, the secondary, device. There are 5 main components. So that architecture is called von Neumann, the basic architecture. What is the goal of this, the von Neumann architecture? Most of the computer systems, the data should be loaded into the memory first. And then part of the data is read from the memory to the CPU, and then working with some operation, and then send back the result to the memory. So this is the von Neumann architecture, like this kind of PC, and then the server, whatever, based on this architecture. The important, sometimes when you click very heavy file, it doesn't show up instantly. It takes about time. Some hourglass is circulating. Why? When you click that file, very large size file, that should be loaded into the memory first. So that's why it takes time. So hourglass is circulating. After loaded to the memory, and then we are able to use that data loaded in the memory. Okay. So think about that. We have a lot of data, like 1 million, 2 million, 1 billion record in a table. So in order to use this kind of table, we have to load very large size file into the memory. It takes time. Performance, in terms of the performance, is not good, right? So we have another approach to reduce the time, okay? So in short, maybe index table and the hash, and yeah, those two approaches can be used to reduce time. That means to reduce loading time into the memory. Okay. Prime memory, you know that, and the secondary memory, like hard disk drive, SSD, you know that. I assume, right? Right? Okay. Okay. So next, how disk, hard disk drive works. Okay. The disk come in a variety of types and capacities, like a multiplatter, then aluminum or ceramic disk, the removable external hard drive, and so on. In short, of the old, the model, but it looks like that. Okay, so those kind of the platter is called a disk, and the disk are stacked together, and the mounting the central the spindle. Okay, and then important thing is the platter, the disk, have a metallic coating and magnetized. Okay, so usually the hard disk drive doesn't use electric field. So hard disk drive use a magnetic field to store bits. Okay, let me show if I have time. I'll show the video. Okay. And then how the hard disk drive works. Basically, it is called the ARM mechanism, access ARM mechanism. So there are one access ARM mechanism with ARM that can reach in between disk. So there is ARM like this. And then the end, there are head for read, for write. Okay, one is for the surface above. The other one is for the surface below. Have you ever seen before this one? No? Okay. Maybe, okay. And then, and also that disk is spin at a very fast, very high velocity. So sometimes when you hear the sounds of the machine, there's something, there are sounds, kind of spinning sound like that from the hard disk. And just for reference information, this is a read-write head. This is head, it's triangle, and then this is a surface of the disk. So very narrow. And compare with other human hair and smoke particle fingerprints, it's much thicker than the space between head and then surface of the disk. Okay, so when you touch the disk with your hands, probably the data will be damaged. Okay, the head cannot read because of those kind of dirty. Okay, and then so the disk is divided into several areas. For example, track. So track means concentric circle like this. Okay. So from the outside, this is a track 0, track 1, and track 2, 3, and track N. And also, additionally divided into like a track and the disk sector like this. This kind of the picture shape is called the disk sector. And this couple of, and the track sector is this one, small part. It's called the track sector, and the couple of track sector called this cluster to store the data. Okay. Then the arm is moving to store and then read data, the specific track sector. So, question. So we are able to store in a hard disk drive those kind of track sector. We are able to store data like this. Okay. But if you have a very large size is the file, how would you store the record of a large file on a disk from this? Very large. If the record is small, maybe you can store just one single track sector, but maybe 1 megabyte, 1 gigabyte, too large. How we are able to store? Maybe one option is to fill up the first track, like track 0, store data. And then if the track 0 is full, go to the next track 1. It's full, go to the next. Go to the next. What do you think? Is it reasonable? Or something wrong? So looks like reasonable. Yeah, you can do that, but there are some problem. Why? Every time we move from one track to the next, device access arm mechanism has to move. So the arm is moved. But think about that. The speed access arm mechanism movement is mechanical, but the CPU and the main memory communication is electrical processing time. Which one is faster? CPU and the RAM is much faster than the mechanical the movement time. That means the CPU sent a request to order, please read the data, but the CPU should be waiting for a long time. It's inefficient until the ARM access mechanism finishes its job. So to reduce this time, another concept, the cylinder, is introduced. What is a cylinder? So cylinder is collection of tracks, which means it's a disk, maybe it's a couple of disk, like a platter, so that. And then there are tracks like this. Okay. So what is that? Collection of a track. This is a track 0. And this is a track 1. This is a track, maybe it is a hole, something like that. So draw imaginary line, like take a look at the track 0. You can have this kind of, looks like the cylinder shape. That is a track 0. And there's another cylinder with the track 1. Another one is a little bit smaller. This is a track 1, like that. So we have 2 cylinders with track 0 and then track 1. Okay, there are 1, 2, 3, 4 the disk, and also there are 4 disks, something like that. So in order to store and then read the data, use this cylinder. How? As you can see here, we have arms like this. And then in the end of the arm, there are heads. So when you write and then read the data at the same time, simultaneously read here below the first disk, and then surface of the second disk, and below, above, below, above, below, above. So we don't store data like this. Instead of that, we store same data, the below here, and the above, the below, above, below, above, something like that. So if we have the table like ID, name, address, something like that, these kind of data are stored, saved, these parts, this part, this part, this part, this part. And then when you read, we use ARM, the head. So at the same time, almost no time, we can read. We don't have to move the arm. to find this location. That means we can reduce the time and the parallel. Make sense? So yeah, that is that I mentioned the concept of the cylinder, how to read and how to write. Okay, so please take a look at the PowerPoint downloaded in the D2L. So more detailed information is there. So why cylinder is important? When you try store data, retrieve it on a disk without having to move the arm mechanism, just turn on, turn off the heads. So this is electric switch, so almost no time. Okay, like that. So it reduce time. Then this is for just for your information. To find and then transfer data, we need those kind of time. The sixth time is to move arm mechanism to the correct cylinder, okay? And then head switching time to select read-write head to access the required track of the cylinder. Rotational delay, the platter, the series spin. So waiting the desired data on a track to arrive, okay? The last one, transfer time. So add all those kind of the time. So that is related to the performance, okay? Okay, so the disk works like that. And then think about that. If we store data somewhere in a disk like this, and maybe 1 month later or 1 year later, I'd like to find maybe here we store Christina's ID, maybe 101. Maybe 1 month later, try to find Christina's ID 101 from the city. How we are able to find 101? So in order to do, we need file organization and then access methods. So those are two concept techniques for how we store and then how we retrieve. So file organization is the way we store data, access methods, the way we retrieve the data. For example, if we remember the exact location in a city, in a platter, maybe 1 month later, we are find directly without the consuming time. We don't have to sequentially search. Maybe the address of this one is like 12222. If we know the address, we can go directly that position and then just read the data 101. It's the same. So in here, we use the index and the hash. Okay. So two ways of achieving data access, index and then hashing. So what is the index? What do you think? What is index in a book? Have you ever seen index? Yeah, that's right. That is the index. It's the same. How index consists of? usually maybe some terminology like which one is good? Bubble sort, like item. And then what? Page number. Maybe page number 123. And maybe insertion sort. Maybe 256. And quick sort. Maybe 445. Looks like this, right? The item, page number, and then what? Those are alphabetically sorted, right? So when you try to find like the bubble sorts, go to the end of the book and then find the bubble sort. And then, oh, there's 123. Go to the page 123 to find the bubble sort, right? So the same concept. Make sense? Okay. Similarly, in a table, it's the same. Take a look at the red box. What is this? Salesperson number, salesperson name and city, and other columns. This is a table about salesperson. So we use previously a couple of times, right? And internally, the DBMS creates another additional table called index. Okay, so take a look at the green box here. So in this index created by with the two columns. One is that the column salesperson name here. And then another column is a record address. Record address is a physical location where that data is stored in a hard disk drive. Okay, so previously in the record address represents like this. Cylinder 0, track 1, and track sector maybe 2. Those kind of information is used for record address. But these days, we use a relative, the record number. So for example, so this is a record number 1. This is the first row. And this is a 2, the second row. This is a relative, the record number. And then maybe salesperson number is alphabetically sorted from there, and then Adams with the first. Okay. And what is the record number? It's 3. So Adams and then 3. Next, what? Baker. The second. So Baker. And then record number is 2. So 2. And next one is Carell. Will be 6. 6. Next, Dickens and 4. Dickens 4. So in this manner, create the index, right? So think about that. Instead of loading those, where is it? These big, large sized table into memory, the small size of the table is loaded to the memory. So we are able to reduce loading time, and then we are able to easily find the specific record. For example, if we want to find the green, so green is the record address is 7. So directly go to the 7 and then find the green's number, city, commissioner percentage, and so on, address, just like this. Okay, so this is index table. And this index built over the city fields. Any kind of the column can be used to create this index. In this case, the city index, alphabetically the sorted. The first one is Atlanta. This is a 5. Next is Dallas 3, Dallas 3, and Dallas 4, Dallas 4, and Detroit 2, Detroit 2, this order. So this index rotated into the memory, and if we want to find specific data about the city, take a look at, refer this index table. Maybe Atlanta, go to the record address 5 directly, then can find the records of Atlanta. This is a index table. And another one, think about that. Create the index using salesperson number. So in the salesperson number, in a salesperson table, salesperson number is already sorted by number, right? Then the record number, like this. So when you create index using salesperson number, you can have those kind of index table. And this is a sorted, and then this is a sorted. So that is called the indexed, the sequential, the file, the specific case. So if you have this indexed sequential file, we are able to can search sequentially and then directly. The two approaches are possible if you have this indexed sequential file. So here, questions. If you have a one table, so up to how many index table we can have? Assume that we have just 3 columns: salesperson number, salesperson name, and then city. So what is the maximum number of index you can have? Can have the max up to 3. So the first index by with number, second index with name, third index with city. Can have the 3 index tables. Okay. But there is the problem. Think about this case. New salesperson French, and then salesperson number 452 is added to the table. After that, after updating table, we also update index table, right? But in an index table, this is alphabetically sorted. So the French is F, should be located placed here between D and G. Make sense? And then this is a record address is 8. So branch A inserted here, here. So, but in order to insert French and 8, what should do? We have to shift down the existing data. Taylor, shift down. Lincoln, shift down. Taylor's position. Then green, shift down. And then make empty space. And then to this, we insert French and 8. Right? But assume that we have 1 million lines here. So in order to insert French 8, how many strip downs operation we have? 1 million times. 1 million times. And then make available space and then add here. So 1 million times operation takes time. Okay. So it's a simple but some problem when you update or when you delete one of them. Delete Carrel 6 from the index. We have to shift up all the data, right? It takes time. So instead of the simple linear index, we use a B plus tree index. You know that the tree data structure? Yes, no, no. So have you ever seen maybe something like that? Isn't this kind of data structure? That's a tree. So usually each node has up to 2 children node, the child node. It is called the binary tree. So into this node, we can save the data. Maybe 1, 2, 3, 10, 12, 31, 40, something like this. You can store the data into the node. Okay, this is the node, and another word is called the root. And this is a leaf. Okay, this is a layer. Layer 1, 2, and 3, and 4. In other words, it's called the depths. So those kind of code is a tree, especially a binary tree. But in a database, kind of the variant of the binary tree is a B plus tree. In a binary tree, node can have the children node up to 2. Left child. Okay. Show. Okay. So, see. This is a P plus tree index. Root, and then node, and then reef. Root, node, and those kind of the node called the leaf. Okay. Then, so this is example. Maybe, gosh. Take a look at this one. So what is that, this one? It's a cylinder. There's a cylinder. So cylinder is what? To store data, right? Especially in the first cylinder, and then there are cylinder 1 and the cylinder 10. That means we have the flatter, the multiple flatter, and then there are how many tracks? Total 10 tracks from 0 to 10. So we can create the cylinder. Cylinder 1 means it's a track 1. Cylinder 2 means this is a track 2. Like that. So we are able to save the data above, below, the same track. Okay. And in this case, salesperson number between 81 to 140, those numbers are stored cylinder 1. And 145, 192 store cylinder 2, cylinder 3, 4, 5 until cylinder 10. Okay. And then take a look at this part. This is a node, especially that is called what? Root. And the next layer, lower layer, there are how many nodes? The 3. And then in each node can have there up to 4 key and value pair. So this is the first element, second element, and third, and then fourth. Okay. Right? And so 140, 192, 256, 53. So what does then mean of these numbers? Can you find some characteristic? Those numbers are from where? Salesperson number. Okay, especially 140, 192, 253, 140, 192, 253. Okay, 307, 307, 368, 416, 477. What kind of salesperson number? Max, the highest, the salesperson number. So the highest salesperson number is inserted to the node. And then this is a key, and this is a value. Value means the pointer. That number salesperson less than 140 store cylinder 1. 192, this one. The less than 192 salesperson ID store the second cylinder. And how about this one? 253, less than 253 store the third cylinder. Make sense? And how about this? In a root, 253, 477, 641. What is this number? Yes, that's correct. 253 here. So this node, 473, 77, is the maximum, the key value. This is second node. 641, the maximum key value. Pointer, this node. Yeah, that's a rule. So if you have some data, data are stored in each cylinder, and then find the maximum salesperson number, and that number are inserted into the node, the tree, tree. And then this is a key, and then pointer is pointing to the cylinder number, which is cylinder number. So that is a P plus tree. So one more thing is that P plus tree is a balanced tree. So balanced and unbalanced means, for example, when you store data, 1, 2, 3, 4, 5, maybe you can store 1, 2, 3, 4, 5. This is a tree, right? And there are 5 elements are stored into a tree. How about 1, 2, 3, 4, 5? It's also a tree. But what is the disadvantage in this case? If we want to try to 5, how many comparison we need? 1, 2, 3, 4, 5. To find 5, we need 5 times the comparison we need. How about this case? 1, 2, 3, just 3 times. That means we can reduce number of comparison related to the time. So it is called unbalanced. This kind of type tree is called the balanced. And then B plus tree is balanced. Okay? So example of the balanced tree is maybe AVL and red, black tree, and so on and so on. Okay? So this is a balanced tree. And then one characteristic is that the cylinders are connected from the left to right, like this. Like this. But in a binary tree, there's no connection. But in the B plus tree, there are some the connection between cylinders and cylinders. Okay. So think about that from this example. I'd like to find 361 salesperson ID. How we are able to search? To find 361, start from the root and then find the key value greater than or equal to 361. So I'd like to find 361. And from the first key, 253 is greater than 361? No. Go to the next. 477 is greater than 361? Yes. Okay. That key will be located, included in the second element, and this is key, and then value is pointer. So that one is indicating the second node. And then again, repeat, compare. 307 is greater than 361? No. Go to the next. 368 is greater than 361? Yes. Okay. Select these elements. What? The pointer is where? Cylinder 5. There. And then repeat this, the procedure. After that, you can find 361 in the cylinder 5. Okay. So instead of loading those kind of the data, all table data into the memory, this B plus 3 is a more small size and then simple. So if we wrote this table into memory, we easily find the pinpoint the exact locations. Okay, so the loading time is reduced, then easily find the which cylinder 361 is stored. Okay. So this is an example of insertion. So it's the same table, same figure. I'd like to insert 365. We are able to insert 365. It's the same procedure. From the root, compare. 253 is greater than 365? No. Go to the next key. 473. Yes. Okay. Pointer is indicating second note. Then repeat. 703 greater than 365? No. Go to the next. 368 is greater than 365? Yes. Okay. Go to the cylinder 5. And then repeat the same procedure and then find the exact location and store 365 there. But what happened? Cylinder 5 is already full. There's no empty space to store 365. How? So in this case, split. Previous table, cylinder 5, 310 to 368. And it's a full. There's no empty the space to store 365. So as you can see here, split two tables. That means use another cylinder. Okay. So maybe 365. So in this case, 310, 330. 310, 330 for the existing cylinder 5. And 332, 368. Use a new cylinder, for example, 11. Okay. So what's the problem in this case? Here, sorry. In a second node in a B plus tree, where is it? Okay, here. So each node can have up to 4 key and key value pair. The previous It's a 307, 368, 416, 477. But in this case, we split. That means we use another cylinder. So the maximum, the salesperson ID should be inserted into the node, right? So in this case, 307, 330 from this one, 368, and existing one, 416, 477. 1, 2, 3, 4, 5. Make sense? Really? Why? Each node can have up to 4 key value pair. It's already full, but it's 4 pairs, 4 elements, but it's 5. It cannot. So how? We have to split the nodes. How? 307, 330, 368, and another node, 416, 477, empty. But in that case, it's an empty one. Make sense? So the last thing we have to, how about the root? 253, 477, 641. The previous example, this case. But this node is split into 2 parts. So the maximum, the salesperson ID 368, 477 should be inserted into where? Root. So root should be changed 253, 368, and 477, like this. So finally, the root is updated. So the second node, middle node, split like this, like that. So if that root is full, but another node should be added there, that root is split again, and then create another root. If that root is full, should be split, and then create another root. So layer is increased. Make sense? Okay. So that is B plus 3. Okay. Hash sheet. Okay. Just briefly. Have you ever heard of hash sheet? Hashing function. Hash code. No? Okay. This hash sheet is to determine where to insert the particular record of file. The record key value is converted by a hashing routine, hashing function. Okay, so maybe we'll take a look at this one more detail next week. Okay. So division reminder method is very simple and the famous hashing routine or hashing function. So think about that. This example. So here we have Before that, hashing function I'd like to introduce. If you have 10 like this, 0, 1, 2, then 9. So in order to store specific number, it can be done like this. Maybe this is a what is this? It's operator. You know that. Addition, subtraction, multiplication, division. What is this? Yeah, reminder. So maybe 11. What is this? Will be 1, right? So the 11 is store index 1. Why? The reminder is 1. How about 13? Reminder 10, 3. So the 13 store to index 3, 13, like this. That is called hashing. Hashing function, very simple. In this case, division, reminder. Okay, so the division, reminder, the hashing function. The same concept. In order to store salesperson number into the record table, we use this hash function 50. We assume that we have the 50 rooms. So salesperson ID 361. Reminder 50 is what? 7, maybe 11, right? Okay, so record location 11, 361, carrier, and other store there. And 186, find the 50, what? 36. Okay, go to the room number 36 and store there, right? How about 436, 50, 36. Uh-oh, 36, 36. 36 already occupied by atoms. It is called collision. So we have to find to avoid collision. So in this case, we have, so space for overflow records. In that case, I'm sorry. (51 to 54), from 50 to 54 is for the space for overflow. So 36 occupied atoms, but the James for 36 is a 36. In this case, go to the overflow space, okay, and the 50. And then synonyms, the pointer is indicate here. The 50 means the James, if the collision is occur, that data is sent to 50, so let them know. 50 goes to 50. Then how about 236 modular, reminder modular 50? It's the same 36. It's a collision occur, right? Go to 50, or is already occupied the James. So send 51 and then set 51. So this is one of the way to avoid the collision. Okay, but there are several the way to avoid collision. Maybe next week I'd like to introduce like a linear probing, the quadratic probing, double hashing, and the separate chaining, and so on and so on. Okay, so important thing is this hashing can be used to create like the access mechanism and then the file organization. So if you have those kind of hashing function, and then if you know, so 11 is store 1, 13 is store 3. If you want to find 13 from the table, how we applied 13 modulo 10. These are 3. Go to the directly room number 3. You can find, read the data. This is a direct access. We don't have to search from the first room. No, 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 or yes. What happened? It is a million arrays. Maybe the key that I want to find is there. Without direct access, we have to search. That means 1 million comparison we need. It takes time, the computing, the resources. But this is a hash it, the approach for the direct access. Make sense? Okay. So almost there, but maybe we'll continue. Then about this, I'd like to introduce, but this is a simple, not difficult to understand, I think. Okay, I'm sorry. So any questions? Nothing? Okay. Synonyms pointer. Yeah, the end. Yes, yes. But if the collision occur, and so that space, that room is already occupied, find the space for in the overflow space. Oh, and that space, we store that element, and then the synonyms pointer set by -1. This is the end. Okay. If the collisions occurs many times, we set go to the 50, 51, 52, 53, and then the last. So the end of is -1 negative, whatever. Okay. Okay, thank you. And then have a great evening, and then see you next week. So next week is the last class. Okay. So Macon campus, do you have any questions? The Gregory? No questions? Okay, so thank you for attending the class. See you next week. Bye.